Now we look at example 3, in which we have a horizontal surface, a fixed support, a spring on the ground or on the table, a mass m attached to it. X equals 0 is the position where the spring is unstretched and uncompressed. So that's the equilibrium position of the spring, or equilibrium length of the spring would be up to here. And then we pull the spring up to this point, which we call X equals, let's say, A. And then it is released. So because there's a restoring force, it will cause the mass to accelerate towards the left. As it moves closer, the force gets smaller, the acceleration gets smaller, but the velocity of the particle or this object gets bigger because it's still accelerating. So it reaches m, and then it overshoots and keeps going until it reaches a point equidistant from the other side. So that's X equals also, well, this minus A. It comes up to here, and then it goes backwards. At that point, the force is large enough to have stopped it and pulling it back towards the mean position. So it will keep on oscillating. Now the question is that if it starts from here, what is the speed of this mass when it crosses any given point? So let's take that point to be here. Okay, it could be anywhere. So this is our X equals X. Let's say X final. So this is our final position. It's not the final in the sense that it stops here, but it's final in the sense that that's where we want to find the velocity when it's going this way or the other way. Okay, we find the speed when it's crossing this point. It turns out that in the absence of friction, the speed with which this object will be crossing this point while going left will be the same as the speed at the same point when it's moving to the right. So the two speeds would be the same. The velocity would be the same in magnitude and opposite in direction. So this is our initial position, and this is our final position. And now we write the equations. The given quantities are m, the spring constant, the value of a, that's how far we brought it, and the x final, the position where we want to measure the velocity, calculate the velocity. And the question is, what is speed at x final? So we write the equation delta k plus delta u equals the external work minus Fd. Okay, in the first case we'll assume that the friction is 0, so there's no friction, in which case this will be 0. There's no external force because after pulling it here, when there was external work, but after that, once it's released, then it keeps going by itself. It's an internal force, so there's no external force. And now we will write this. So the delta k will be k at the final position will be k here at x final minus k initial, which is the k over here. The the u could be either ug or u spring. Now because the level is horizontal, the ug final and ug initial are the same. There's no change in the y direction, and therefore the delta ug is 0, and the only one we have is delta us, and so that's going to be the u spring final minus u spring initial, and the u gravitational is 0 in both places. So k final is going to be half m v final square, which is what we're looking for, minus half m v initial square, which if we release it from here, that would be 0, plus the spring final will be half k x final square and half k x initial square. Now x final is negative of this value, so you put a negative, but when you square it, it becomes positive. And well, let's go further. So the half is present in all of them. We can cancel that out, and so vf square, we will be bring this on the other side, and we can write it as minus of k x final square minus kx initial square, and divide by the m. So that's what we get here. Now it doesn't look nice to be square rooting a negative number, so we can rearrange this, get the k over m outside, x initial square minus x final square, and square root. So that will be the v final at this point. When we take the square root, we will get two answers, a plus and a minus. So the negative one would be when it's going to the left, when it's going this way, and after going to the right, the positive would be going to the right. The magnitude would be the same whether it's going to the left or to the right. The speed is the same. Now when it's going to the left, we get the negative, and when it's going to the right, we get the positive. The speed is the same in both cases. Now if it were an equidistant here, so whatever is this distance, if it were here, well, the speed here, this has no knowledge of whether it's on the left or the right, because if you put it's minus fx minus xf, it still becomes positive. If you put plus xf, it's still the same. And so the speed at this point, at the same distance on the right side as it is on the left side, the speed here would also be the same as the speed here. So if this is 1 centimeter away on this side or 1 centimeter away on this side, the speed while going to the left or the right here would be the same as the speed going to the right or to the left here. All four speeds would be the same. So this is what we get for no friction. But suppose there is friction, then and let's not worry about this for now. So we'll just consider this point. So as it's going here, it will cross it with some speed, but when it's going back, it should have a smaller speed because friction is going to slow it down. So let's see what happens if friction is not 0. In that case, we would have kf minus ki equals this, equals a value over here. So let me write that out. It's going to be kf minus ki plus u spring final minus initial minus fd. And this d is the distance that it travels from A to here. And when it's going backwards, the d would be from here all the way to here plus this distance, because friction is non-conservative, and so all the distances would add up. This reduction in velocity while going to the left is not recovered in a non-conservative force. The spring force is conservative, so whatever is the loss here, it gains it exactly back by the time it reaches the same place. So the speeds are the same, but it will continue to lose work due to friction. Now, because it's horizontal, the normal force is upwards, the mg is downwards, there's no other component, so the normal is simply mg, and therefore the friction is going to be mu times mg. So we can plug that in here, and then we have the rest of the equation just as we had before. Half mvf square minus half mv initial square plus half kx final square minus half kx initial square equals minus mu mg times the d. So when we're going from here to here, the d is going to be x equals a minus of x final, and here x final is going to be a negative number, so it's going to add up and give us the total distance. XA would give us this distance, and then we add this distance to it. And now if the initial velocity is 0, and we know the initial and final positions, we can plug that in here. We know all of these, and we can get the V final. And it's going to be smaller than what we got from here, because friction is going to reduce this value. And if we want to write it out, we can write it as half mvf square, and take this on the other side. It's going to be half k x initial square minus x final square on this side, and minus mu mg, and well, let's write x initial minus x final. And then we can simplify it further to get vf square equals this would become k over m xi square minus xf square, which is what we had over here, but now we have this additional term 2 over m mu mg x initial minus x final, and the whole thing square rooted to get vf, and we'll have plus minus. Well, we have to be very careful here, because when we're going backwards, then the distance would have to be the total distance up to that point.